Hello everyone and welcome to topic 9 recurrent neural network applications. So far we have discussed and learned what is the recurrent neural network and backpropagation through time. Also we learned the long-term dependency which happened and it is a problematic for the conventional recurrent neural network, and as a solution we introduced like modern recurrent neural networks such as LSTM, gated recurrent unit, and also bidirectional RNN. In this video, we learned the RNN application in mostly in computer vision, natural language processing, and audio. And also, we will discuss and introduce encoder-decoder architecture, which is also like an introduction for attention mechanism and transformer. Moreover, in topic 9, we are going to discuss about autoencoders as well. Well, in this video, we are going to discuss about what makes a recurrent network so special. Previously, we have discussed about and learned about the limitation of vanilla neural network or convolutional neural network, such as fixed size vector as an input and also fixed size vector as an output. Moreover, this model performs this mapping using a fixed amount of computational steps. Well, the core reason that the recurrent network are more exciting than like a previous model is they actually allow us to operate over sequence of vector. Therefore, we have a sequences in the input and also the output, or in the most general cases, both. RNNs are very versatile and they can be applied to a wide range of tasks. For example, as you can see here, each rectangle or each square is a vector and arrows represent a function. For example, matrix multiplication. Input vector similar to like a previous lecture shown by the red color, and also output by green and blues or the RNN state. Well, from left to right, as you can see here in the first actually mode, we have the network without RNN. Indeed, here we have the fixed size of the input and fixed size of the output. And example application in this case is image classification or video frame classification. The second application of RNN here is when we have a sequence of the input and also like sequence of the RNN for the processing of the data that we have, but like the output is only one. Example is, for example, sentiment analysis. From the name itself, we can understand that in order to identify the sentiment based on the review. For example, the task is simply classifying the tweet into positive or negative sentiment. Here, the input, which is the tweet, can have like a various length. And the recurrent neural network took this actually as a vector, and then we have always an output which is like a positive or negative. Similarly, we can actually think about document classification or video classification when we have different video frames as an input, but we would like to analyze whole the video together. Or for example, in this case, we can even name like a 3D image processing when we would like to classify MRI images into one label. Visual question answering is also another example and use case which we can put it in this category. Well, visual question answering systems attempt to correctly answer questions in natural language regarding an image input. The broader idea of this problem is to design and develop a systems that can understand the concept and content of image similar to how human does. And here we communicate effectively about the image in natural language. For example, as you can see here in this picture, we would like to know which type of vehicle is in the current image. Well, one example is the work which actually has done by Raghuar et al. In 2015. Well, here the network has two paths. One path which is actually composed of the CNN layer for understanding a local feature and also global feature from the input image, and also another part of the network substituted by LSTM layer. Here, for example, we have different LSTM layer in order to process the question. And afterward, for the first pass, we have like a embedding vector with the size of 10,000, 1024 for the from the images, and also one similar with a similar size one from the text or question that we have, and then concatenate them. And here, the one of the novelty here is they actually did this using the pointwise multiplication, and afterwards they have one fully connected layer and softmax. And for example, in this figure we would like to know how many horses are in this image, which the answer is 2. Another application and use case of RNN is when we have a single input, and we would like to map this single input to the sequence of the output, or in another word, our input is going to map to different output values. Well, the example applications are, for example, image caption. When the most of the image captioning network composed of the CNN and RNN, where this network actually use CNN for processing of input image, and in case of the image captioning, and the RNN is used for to provide a description of what exactly is happening inside of image. Well, CNN extracted local and global feature and does the for the from the images, and RNN then use this information to recreate the description. Another example is video tagging, where the RNN can be used for video search. And here, for example, we can do image description of video, and then we can divide it to the numerous of the frame. Well, one of the famous image captioning study or network architecture is show and tell, which actually the work done by Google in 2014. In this paper, or in that paper, they use a generative model based on deep recurrent neural architecture, which combine both computer vision and image and machine translation in order to generate a natural sentence which describe the image. And here the model is trained to maximize the likelihood of the target description sentence given the training images. Well, the training process is end to end, and the images or image itself is the input of the Google Net architecture, and then at the end of the at the end of the Linux architecture, the embedding layer pass to the several LSTM layers. And all LSTMs also share the same parameters. Well, they named the architecture as a NIC or NIC, and train it end to end automatically for machine translation and image caption. Well, here these figures actually shows the result of the human evaluation of description provided by NIC model. And first column shows where the model predict everything correctly and without error. It is interesting to see, for instance, in the second actually figure, as you can see, how the model is able to notice the frisbee given its size, because the frisbee is very small, but it's correctly detected. Well, the second color describe the result with minor errors. For example, if we look at the first first image in the second color, as you can see here, it says like two dogs play in the grass, but they are three. And the result for the third column is somehow related to image, and I mean like, but like not correctly, not 100% correct. And the fourth column, the result or the caption which generated for the fourth column is not really related to image. For example, the second actually prediction, it says a refrigerator filled with lots of food and drink, but there is no refrigerator. Yeah. Let's see an overview of RNN application for the language modeling or sequence to sequence learning. In this example, the task is to learn character probability distribution from input text. Suppose we have a vocabulary of four possible letters of hello, which is H, E, L, and O. Here we want to train an RNN on a training sequence of the hello. Well, to this end, we need to create a one-hot vector of for each letter, first of all. And here our architecture at each time it takes the one letter, and the output is the probability distribution or a softmax over four possible characters that might be follow the current input. Well, for example, for the first time step, we need to calculate the probability of E should be likely given the context of the H, and similarly for the L should be likely in the context of HE. And for the second L also need to we calculate the probability given the context of each HEL. And finally, for the O, we need to actually calculate the probability of O when we have the text or text of the HELL. Okay, to this end, like we have the input, which we first of all we need to like create the one hot encoded input. Well, we have four characters, therefore our one hot encoded vector is like it has a like a one in four, and for the first letters we have 1000. Then this one hot encode pass to the like recurrent unit, which can be like a LSTM or any type of the recurrent neural network with a specific weight function of U. And here, for example, our recurrent unit has three neurons in the hidden layer. And afterwards, we have another like a weight function of the V from the hidden to the output. And our output also has like a four output neurons. We have also four parameters here, which these parameters are learnable. I mean, these parameters from the hidden layer and also output layer. These are the learnable parameter, and it can be learnable during the training process. And then our target is E when we have the H as an input. Similarly, for the next character, we have H and E as an input. We need to first create one hot encoded input. For the second letters, we need our one hot encoded input is 0100. And again, we have the specific weight function of the U, and by having U, we will have the three neurons in the hidden state, but this actually neurons in the hidden layer of the recurrent unit has also affected by another weight function of the W, which comes from the previous step. Again, similarly, we have the weight function of the W from like a hidden unit to the output. And similarly, we have the four output neurons here, and here we would like to target or predict the character of L, where the input is HE. And similarly for the L, the probability of the L should be also high when given the context of the input is HE. We have the second L, and after the second L, we would like to predict the O, which is the last character or last letters. And during a training process, we would like to increase the confidence for correct letters, which indicates the this actually weight function, which we show it by the green arrows, and decrease the confidence of all others. And this is the one example for the language modeling or character level prediction. The previous example was very simple, but like in reality, typically the embedding space is a much higher dimensional space. As you can see here, the two-dimensional embedding space for the word level. Well, in this level, instead of one hot representation of words, it's like a standard practice to encode each word as a dense vector of the with a fixed size, which capture the underlying semantic context. As you can see here, the similar words are embedded close to each other in a lower dimensional space. Well, the dimensionality of this embedding is usually much smaller than the number of words which we have in the dictionary. And using this can give us like a good overview and good starting point for different NLP tasks. And it is also easy way in order to incorporate prior knowledge into the model. And also it's also can be a primary step for transfer learning task as well. In the machine learning community and deep learning community, there exist different approaches in order to learn word embedding, but like the most popular one is Word2Vec, which developed by Google, and also Facebook has another library with the name of Globe, which actually they are very famous and easy to work with them. These embeddings are typically between from 100 to 1000 dimensional space. And maybe another point is here, like this embedding can capture the meaning of each word to extend the meaning as well, but they do not capture the semantic of the word in the given context because each word has a static which can be computed with another word. For example, depending and the context, the name of for example, the word of bank can be referred to a financial concept or uh, to be a specific name like a river bank. And the last part of the RNN application is when our network takes a sequence of the data or many inputs, and the output is also, we have many outputs. Here, the network architecture designed to predict a sequence from a sequence. Here, the length of the input sequence can be varied with like a output length of the sequence. Application like chatbot or machine translation, event classification can be like a category in this. Or can be like an example for this type of recurrent neural network. Or I explained the application of sequence to sequence type 2. It's important to know another concept as the encoder decoder architectures here, which is also related to this topic. For different applications such as question answering, dialogue system, chatbot, machine translation, our network needs to predict the output sequence different from the input sequence. And this is the job for the autoencoder or encoder decoder architecture, which has a different name such as sequence to sequence architecture. And using this, we are able to actually design and build a network for doing this. Here is a schematic of encoder decoder network. As you can see here, the task is machine translation. We would like to translate the sentence in English to Deutsch or German. Here we have the input with the size of 4, where we map it to output in the size of 3. Well, first we actually create the one hot vector for each input and then pass it to the encoder part, which is, for example, any type of RNN can be LSTM or different type of RNN. And here, the last actually At the last or the final hidden state pass the information from encoder to decoder part. The decoder shown by here, I mean the decoder neuron shown by pink color here, and we call it here G. And then the G maps the information from the input to output, and here we predict the loud and dot at the end of sentence. Well, specifically here in encoder-decoder architecture, an input or encoder RNN process the input sequence with a specific length of the, for example, here 4, and then compute a fixed size or a fixed length of the context vector, which you can see here. We show it by z of the t, but you can see, maybe you can see in the different literature with the different notation. Usually they actually use it with a C as well. And the final hidden state pass the information from encoder to decoder. Similar to the conventional RNN here, one time step after other information pass this actually information to the next hidden unit as well, and pass it to the forward in the time, and using, for example, any type of the recurrent connection. And at the end, like a context vector summarizes important information from the input sequence. For example, the intent of the question in a question answering task, or like a meaning of a text in the case of the machine translation. And then decoder RNN uses this information to predict the output of the sequence with a specific length. And this is not necessary to input sequence be same as the output sequence. Well, yeah, this is what I actually explain and talk about this. In the case of the machine translation, well, in the task of the machine translation, the decoder is a language model with a recurrent connection between the output at one time step and the hidden state at the next time step, as well as recurrent connection between the hidden state. Well, we can show it like this. We need to calculate the probability of the output, which we show it by y, and also by in order by given when we have a like a given input information of the sequence x1 till xn. To this end, actually, we need to calculate the probability of the y at time step t by given of the context vector of c, which we can see here. And the architecture jointly trained to minimize the translation error given a source sentence. And each conditional probability actually can be calculated using this formula, where the f is nonlinear function, and the in case like it can be also, for example, tonnage or other type of like a activation function as well. Well, G of t is the hidden state of the decoder network architecture, and C is the context vector. Okay, let's see more example, and in case of the application of the RNN or encoder decoder network. Here is another example for neural machine translation sequence to sequence learning with neural network, which actually developed in 2014. As we saw earlier, an encoder converts the like our input or sequence input to the like a vector or meaningful vector, which we call it context vector, and context vector later on takes by decoder architecture or decoder itself is again composed of the series of the recurrent unit, and then we can predict the output with the different sequences. Well, encoder and decoder architecture can have a more than one layer, as you can see here in this example, has a two hidden layer. Another example is generating with a recurrent neural network, which they use also similar architecture for doing this. And the top row, actually, you can see the real data, but the This actually rows, as you can see here, these are generated by different RNN architectures. Well, for this type of task, we need to use the generative model in order to, they need to learn the like a distribution of the data. For example, in this case, this type of, text or handwritten text, and when they can learn the data very well, data distribution well, they can generate also at the end something similar to like a distribution that we have. Well, another use case is for audio data. In this example, we can see like a combination of recurrent neural network and convolutional neural network used for detecting emotion from signal data. The work done by Anand and Ferma in 2016. Well, in this example, first some local information extracted using the CNN, and then we pass this information to different LSTM layer in order to learn the context. And at the end, we have the different output for emotion prediction. Another interesting application of RNN is for multimodal learning. In this case, you can see the work which actually done by Andrew Owens et al. In 2016. Their network takes like an input of the video frame, and then it can predict the sound for each frame, which is very interesting application. Well, the network architecture actually trained supervisedly, and they try to synthesize like a sound for each video frame. Well, these are the references for this actually part of course, and thank you for your attention.